Hey guys, welcome back to a new video. Today we are solving exercises on calculating partial derivatives of multivariate functions, meaning functions with two or more variables. If you didn't quite understand what I just said, don't worry, because before we delve into the exercises, I will give a brief summary of a couple of concepts that will allow you to better understand what we are doing. As always, the exercises will start out very basic and will get progressively more complex towards the end. The timestamps can be found in the comments below, where you can also ask any questions you might have. So let's start with a brief summary and try to do it under 2 minutes. A function in its most rudimentary form is basically the following. It takes in an input number and gives back an output number, which we call f of x. For instance, for a particular function, we could give 1 as an input number and we would get back 1. If we put in 2 as an input number, we'd get back 4. 3 would give 9 and so on. And you would pretty quickly see that the function prescription in this case would be x squared. So any number that you input would simply get squared to get the output. Then the derivative of a function compares the rate of change of the output numbers with the rate of change of the input numbers. For example, if we go from 1 to 2 in the input, we add 1. And we see that for the output, we have to add 3. Likewise, if we go from 2 to 3, again adding 1 in the input, we go from 4 to 9, whereby we add 5. For this particular function, we see that the increase in output outpaces the increase in input. And this is exactly what derivatives are designed to describe. As you probably know, derivatives also have a graphical interpretation. Let's look at the graph for our function x squared. This is the x-axis and this is the y-axis or the f of x axis. What the derivative does is that it looks at the slope of the curve in each point. Let's, for example, look at the slope in this point for a small x, and we see that it is much less steep than the slope of a point that is much further along the x-axis. And it is in this sense that the derivative of a function measures the steepness of this function in each point. To concretely calculate the derivative of a specific function, we know that there are a list of rules that we can use in order to get the right result. For example, the derivative of x squared simply becomes 2 times x. And because partial derivatives are an extension to normal derivatives, in this video I assume that you know the basic rules of derivatives. For example, deriving the product of two functions and using the chain rule. What are multivariate functions then? These again are prescriptions that take in numbers and give back a single number. In this case, it takes in many numbers, for example, 2 numbers as an input number, but still gives back a single number. For example, let's say that x and y is 1 and we get back 2. X is 1 and y is 2 gives back 5. X is 2 and y is 1 gives also 5. And x is 2 and y is 2 gives back 8. And from this example, you might already see that f of x, y in this case is simply x squared plus y squared. So it takes 2 numbers, it squares both of these numbers and then adds them together. And this gives back one single number. And it is in this sense that this function has 2 variables, x and y, because you can choose 2 numbers to input in this function and to get back one number. And in a complete similar fashion as before, we can now ask the question how the rate of change of our output numbers compares with the rate of change of our input numbers. However, here we see that we have 2 input numbers that can vary independently from each other. Therefore, in the case of a function with 2 variables, we should look at 2 kinds of derivatives. And this is exactly what partial derivatives are. The partial derivative to x of our function in 2 variables specifically looks at the change of the output number f of x and y when we only change the variable x, so the first column in this case, and we consider y to be a constant. And similarly, the partial derivative to y of our function in x and y looks at what the rate of change of our output variable is if we're only allowed to change y, so the second column in this case. This means that for this derivative, we consider x to be a constant. And how we concretely calculate these two partial derivatives of this two-dimensional function, so this function in two variables, is what we will look at in the exercises right now. In the first exercise, we simply continue with the example that we were working with, where f of x and y, so our multivariate function in two variables, is equal to x squared plus y squared. The first partial derivative that we are calculating is the partial derivative to x of f of x and y. And again, as I said, the partial derivative to x means that we're only treating x as a variable and we leave y as a constant. This means that we get the following. So the partial derivative of x squared plus the partial derivative to x of y squared. However, we know that the derivative or the partial derivative of a constant, because we're deriving to x and with respect to x, y is a constant, this term simply becomes 0. And we're left with the partial derivative to x of x squared, which simply becomes 2x. And this is how, for a partial derivative to x, we consider y to be a constant and only x as a variable. In a completely similar fashion, we can calculate the partial derivative to y of our function f of x and y. And in this case, we see that we are deriving to y, so we are treating y as the variable, and in this case, treat x as a constant. Thus, we get the partial derivative to y of x squared, which we know will be 0, plus the partial derivative to y of y squared. And because in this first term, we're deriving to y, and x squared is just a constant, the derivative of a constant is 0. And then for the second term, we simply derive y squared to y, which becomes 2y. And we already see here that these two partial derivatives are different from each other. However, they are both very similar in the sense that they're both linear functions. Let's go to the next exercise, where we look at the function f of x and y, again a function in two variables, which is x plus y squared. And for this particular function, we're going to solve it in two separate ways. So the first is just to leave the function as it is. So let's calculate first the partial derivative of x plus y squared, meaning that we're now deriving to x as a variable and we leave y as a constant. So for this partial derivative, this could also have been x plus 1 squared, because 1 is also a constant. So here we use the chain rule. So we first derive these brackets, so 2 times x plus y, and we have to multiply by the partial derivative of these brackets, x plus y. And of course here we very easily see that this term simply becomes 1, because the partial derivative of x to x plus y, where y is a constant, simply becomes 1, because we get the partial derivative of x. So we know that the result of this function will be 2 times x plus y. Similarly, we can do the partial derivative to y of this same function, x plus y squared, where in this case, we're deriving to y. So y is the variable and x is the constant. So equivalently, this could just as well be 5 plus y squared. First, we derive the brackets. So again, we get 2 times x plus y. And we still have to derive to y these brackets x plus y. And here again, we see that x is a constant. So this basically becomes 0. And we get the derivative to y of y, which is simply 1. So this also becomes 2 times x plus y. And we see that in this case, our two partial derivatives are exactly equal to each other. As I said, we will calculate these partial derivatives in two ways. And for the second way, we first compute these brackets, which we know becomes x squared plus 2 times x times y plus y squared. And this should give the same result. We see that we're deriving to x, so x will become our variable, and y again is the constant. And we see here that we first get an encounter with the product of x and y. However, if we just stick to our strategy that y is a constant, this could easily have been 2 times x times, let's say, 5. So y is just treated as a constant. So we can just derive this term by term. The first term becomes 2 times x because we derive x squared to x. The second term becomes 2 times y because we're deriving 2 times x times y to x. And 2 and the y are constants, so only the constants remain. So we get 2y. And for this last term, we of course get 0 because the derivative to x of y, which is a constant, is 0. And we indeed get the same result because these 2 can be put outside of the brackets and we get 2 times x plus y. Let's do the same now for the partial derivative to y. Again, x squared plus 2 times x times y plus y squared. And this time, as always, the y is the variable which occurs here, and x is considered a constant. So, for example, 5 or 6 or whatever number. Again, this first term simply becomes 0 because deriving x to y is simply 0 because x is a constant in the eyes of y. We add to this second term, which is again 2 times x times y, but 2 times x is simply a constant, so that's the only thing that remains. So we get 2 times x. And for the last term, we simply get 2 times y, because y squared derived to y is simply 2 times y. And we see that indeed we get the same result here again. And by now the general idea is probably clear, so let's go to some more involved exercises. In the following one, we have f of x and y, again 2 variables, which is equal to the cosine of x squared times the sine of x times y. And again, we are going to calculate the partial derivative of x and y to see the rate of change of this function in x and in y. Let's start again with the partial derivative to x of our function cosine of x squared times the sine of x times y. And because we are deriving to x, we only consider the x as being a variable and y is a constant. Therefore, what we get is the following. We have the product of 2 functions with an x inside of them, so we have to derive the product of 2 functions. And this goes as follows. In the first term, we get the partial derivative of our first function, the cosine of x squared, and we multiply this with the second function, the sine of x times y. And then we have the second term where we leave the first function untouched and we multiply with the partial derivative to x of our second function, the sine of x times y. And if this is not entirely clear how I got this term, this is simply the derivative of a product of 2 functions. And I've made an entire separate video devoted to only solving exercises on the derivatives of the product of functions. At this point, we can calculate our derivatives. The derivative to x of the cosine of x squared can be easily calculated using the chain rule. First, we compute the derivative of the cosine of something. In this case, this something is x squared. And we multiply this with the derivative of x squared, which becomes 2 times x. And of course, we cannot forget this second term here, times the sine of x times y, plus the cosine of x squared multiplied with the derivative of the sine of x times y. Now again, this y in this case is just a constant, so it could just have been the sine of 5 times x or 6 times x, and we will derive accordingly. So again, here we use the chain rule. We first derive the sine of something, which becomes the cosine of something, and in this case something is x times y, and then we still have to derive x times y to x, which of course becomes y, because this y is the constant in front of the x. And this is basically already our result, because there are no derivatives left in this expression. So we can go ahead and now calculate the partial derivative to y of this function. And we will see that this will actually be much easier calculation than the partial derivative to x of this function. If we derive to y, we see that only a y appears in this sine of x times y, and all of the other terms are simply constant, so we don't have to bother about them. Because this entire cosine of x squared is constant, it can be put outside of this partial integral. So we get the following. We get the cosine of x squared, which is considered a constant because we're deriving to y, times the partial derivative to y of the sine of x times y. This of course simply becomes, again, the cosine of x squared times, we now derive the sine of x times y to y, so x is simply a constant, so we derive the sine, which becomes a cosine of x times y, and we have to use the chain rule to then still compute the derivative of x times y to y. So again, we get first the cosine of x times y, which is the first step in our chain rule, and then we still have to derive x times y to y, which simply becomes x. And we see that this result is quite more easily obtained than the previous one and is indeed quite different. Let's go to the next exercise where we show that we don't have to cling on to these x and y because they're just names of variables. We could just as easily have a function in the variables r and phi. And phi is a Greek letter that is often used as an angle. For example, here we have the cosine of phi. This is also a function in two variables. One is r and the other one is phi. So again, we can calculate both partial derivatives to each of these variables. The first one is the partial derivative to r. And again, we have our function 1 over r times the cosine of phi. Because we are deriving to r, we see that only this r is a variable and this phi is considered a constant. And therefore this entire cosine of phi is considered a constant. This means that it can be put outside of the integral. So we get cosine of phi times the partial derivative to r of 1 over r. And we of course know what the derivative of 1 over something is. It is simply minus 1 over that something squared. And in our case, something is r. And we're already done at this point for the partial derivative to r. Let's now calculate the partial derivative to phi of our function. We see that 1 over r in this case is the constant, and we are only left with the cosine of phi. So this 1 over r can be put outside of the integral. So we get 1 over r times the partial derivative to phi of simply cosine of phi. And we know what the derivative of the cosine of a variable is. This is simply minus the sine of that variable. So we get 1 over r times minus the sine of phi. And just like that, we already calculated our two partial derivatives to r and phi, showing that we don't need x and y to be the names of our variables. Let's now expand our experience on variables by looking at the following function. We already seen that we don't need x or y specifically as the names of our variables. And now we will see that we also don't necessarily need two variables. We can also have three variables. In this case, we have r, phi, and theta. And the specific function that we have is r squared times the sine of theta times the cosine of phi. And we see that this function requires three input numbers, but still will only give one number in return. And because we have three variables, we can now calculate three partial derivatives. Let's start with the first one, which is the partial derivative to r. Again, our function is r squared times the sine of theta times the cosine of phi. In this case, because we're deriving to r squared, we see that the sine of theta is constant and the cosine of phi is also constant. So we only have to derive our function r squared to r. So we can simply write the sine of theta and the cosine of phi outside of our partial derivative. And we still have to calculate the derivative to r of r squared, which is of course 2r. And we already have our first partial derivative, which was the partial derivative to the first variable, r. Let's now look at the partial derivative to phi. Again, our function is r squared times the sine of theta times the cosine of phi. And in this case, it's the cosine of phi that is variable, because it's only phi that is variable, and r squared and sine of theta are fixed, which means they are constant. So that means that they can be brought outside of the derivative. So we get r squared times the sine of theta, and we're only left with deriving 2 phi the cosine of phi, which is of course minus the sine of phi. And then to end off, we look at the partial derivative to our last variable, which is theta. Again, our function is r squared times the sine of theta times the cosine of phi. And in this case, you know how it will work. Theta is in this case the variable, so only the sine of theta will be the function that we really have to calculate, and r squared and the cosine of phi will be constant, so they can be brought outside of the derivative, and we're only left with deriving the sine of theta to theta, which is very straightforward and just the cosine of theta. And we see that in this case, we calculated 3 partial derivatives of this function in 3 variables. Now, of course, this doesn't get limited to 3 variables. You could have easily have functions of 20 or 30 variables, and they would have 20 or 30 first order partial derivatives. And to end off, let's stay with physics examples and look at the quantum mechanical wave function of a free particle. In this case, the variables are x and t, because we're considering a particle in 1 dimension. And the wave function looks as follows. So we have a times e to the power of I times k times x minus omega times t. And if you're not familiar with any of the symbols right here, just remember that our variables, so the things that change, are x and t, which are here and here. And all of the other numbers, for example, this omega and this k, are related to the energy of the particle. This I is simply the imaginary number I, and this A is simply a magnitude which always can be dropped, so it doesn't really matter that much. However, what matters is that we have 2 variables here, x and t, which means that we can calculate 2 partial derivatives. Let's first look at the partial derivative to x of our function. And our function can be written as a times e to the power of I k x multiplied by e to the power minus I omega t. And what I used here is of course that e to the power of a plus b is equal to e to the power of a times e to the power of b. And this first partial derivative is basically looking what the rate of change is of the x position of our particle. We see that we are deriving to x, so only x is variable here, meaning only this e power really matters. The other 2 are simply constant. Because t is constant, this whole e power is also constant, and they can be put outside of the derivative. So we get a multiplied by e to the power of minus I omega t times the partial derivative to x of our function e to the power of I k x. And what we have here basically is the derivative of an e power. However, inside of this e power, we still have a constant multiplied by x. So we'll have to use a very easy chain rule to take this into account. So we have a multiplied by e to the power minus I omega t multiplied by e to the power of I kx, which is simply deriving an e power, which again gives the same e power, multiplied by I times k, which is a result of the chain rule of deriving I times k times x, deriving it to x. And this is already our result of the partial derivative to x of our quantum mechanical wave function. The same can be done by looking at the partial derivative to time of our function. And our function again is a times e to the power of I kx multiplied by e to the power minus I omega t. And in this case, it is t that is our variable. So it's this e power that is the thing of interest, and these 2 here are constant because x is a constant. So this simply becomes a multiplied by e to the power of I kx, our constant functions, multiplied by the partial derivative to t of our e power with as an exponent minus I omega t. And this is again completely analogous to what we had before. We have to derive an e power. However, in the exponent of this e power, we still have this constant minus I omega, which is multiplied with this t and requires the chain rule to be handled with. This is equal to a times e to the power I kx multiplied by e to the power minus I omega t multiplied with minus I omega, which comes from the chain rule. And in this case, this is our result. And we see that both results are actually quite similar. So if we derive the quantum mechanical wave function of a free particle to its position or to the time, we actually get a quite similar result, which in both position and time are behaving very similar. And this brings us to the end of this video. And I hope that you're now much more familiar with how to calculate partial derivatives and that you now also have an intuitive feeling of what they really mean. As always, if you have any questions or remarks or even suggestions for future topics, leave a comment in the comment section below. If you learned something, give the video a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you guys for watching, and I will see you guys in the next one. Bye.